Thank you. I'm delighted to be with you tonight and to have the opportunity to present this work we've done at Philips Medisize. So thank you very much for the invitation. The use of dry powder inhalers is expanding beyond COPD and asthma, and larger amounts of formulations are needed as their range is increased. Here, the deagglomeration of large payloads, typically between 20 or 100 milligrams, can raise some technical challenges that we've addressed with a concept device called O1. So what's the deagglomeration mechanism? You have a device with a large blister that's pierced as you remove the cover. But what you'll notice is that you have also a mobile cruciform ball in the device. Now, looking at the device from the top, over the mouthpiece, you will find a grid. But under this grid, you will find this cruciform ball sitting in a 3-inlet cavity, 1 inlet for the powder and 2 inlets for air, that we'll call the cyclonic chamber. And the whole point of this presentation is to understand how this cruciform ball and the cyclonic chamber manage to deagglomerate these large amounts of powder. What is the mechanism? How is the powder dispersed by the flow? And what's the impact on performance? And we've addressed this by 2 angles: direct visualization of the flow in high-speed imaging and a rationalization by simulation. So we'll start with the visualization in high-speed imaging. We've tested 2 prototype geometries that you will see on the left, a 2-inlet cyclone and a 3-inlet cyclone. Both have a transparent lower part, which means that you will observe the flow through the cyclonic chamber in the same direction of the mouthpiece. We've used 100 milligrams of macronase formulation, cohesive formulation, and we've tested 3 different configurations with a spherical ball, no ball, and a cruciform ball. Initially, you see the particles being smashed against the walls by centrifugal forces, but the most interesting thing on this video is that the cyclonite in the center and on the left is quite stable, while with the cruciform ball, it has some sort of erratic motion. It moves a bit randomly in the chamber. We've also identified 3 deagglomeration mechanisms. So deagglomeration by shear in the cyclonic flow, impacts of particles against the ball and against the wall. And what you can see on the right is a 3-inlet cyclone. This time you see the cyclonite moving around as the flow goes on, but the ball has also some sort of irregular motion. So we've realized that this motion, you could observe it without powder because it's due to the flow of air going through the chamber. And once you do recordings without powder, you can analyze the images by image processing, apply a segmentation, and record frame by frame the position of the ball. So you can construct the trajectory. So you have 2 typical trajectories. What you can see is that the spherical ball has a very circular motion in the chamber, while the cruciform ball has a very irregular motion, bounces, accelerate, decelerates in the chamber. If you plot the radial position of the ball, you get this kind of signal. So you see a clear difference between the 2 kind of balls. And this time series, you can analyze it with the 0-1 test for chaos developed by Gottwald and Melbourne. And this test helps to identify what the nature of the dynamics you have. You introduce 2 variables, P and Q. If these variables describe a walk that fits in a bounded domain, which is this flower shape that you can see, this trajectory, this is a sign of irregular dynamics that you can see with the spherical ball, so predictable, expected. While on the right, you see that P and Q describe some sort of random walk, which is a sign of chaos. And this is very important because it explains why the cyclonite was so unstable. The dynamics of the ball is chaotic and maintains the cyclone in an unsteady state. As a result, you also have an increase of pressure fluctuation and shear stresses that help the deagglomeration of particles. However, as nice as this is, it doesn't explain fully the story, and we'll move now to simulations to understand a bit further how this whole process works. For these simulations, we've modeled the internal geometry of the device, but we've treated the ball, the cruciform ball, as a static obstacle. And this is justified by the observations in high-speed imaging, because we've seen the particles smashing against the ball, which suggests large differences in velocities between the flow and the ball. Given this large difference in velocities, you can actually decouple the time scale of your problem, treat the ball as an obstacle, potentially vary the position if you'd like to investigate more positions, compute the flow, and then seed the particles from the inlet channel. So that's what we've done. Let's focus on the flow first. What you can see is that without a ball, you have a very high velocity rotary flow in the cyclonic chamber, but the ball deflects the velocity streamlines, in its vicinity. It's even more obvious when you look at the velocities in a horizontal plane, for instance. So you see that without a ball, the cyclone is very much at the center of the cyclonic chamber, but the ball offsets this cyclone, off-centers it, and introduces velocity gradients and therefore shear. And this is actually a very important observation because it confirms that the results, what we've seen in high-speed imaging, is not an artifact from the experiment. It could be a leak or a feature. It's an actual property of the flow that the ball offsets and destabilizes the cyclone. Another effect that you can see is if you look at velocities in a vertical plane, the ball creates an uplift as the flow passes it, and this has a direct impact on the particle dynamics. So to understand this, let's consider a cyclonic chamber without a ball first, and we'll look at small particles on the left and large particles on the right. So that's what we get. The small particles are all conveyed towards the mouthpiece, while you can see a large portion of the large particles is trapped in the cyclonic chamber by the centrifugal forces. Now we'll introduce balls, and we will see what's the effect. What you can see is that the uplift we've seen in velocities creates a scooping effect that deflects the particles towards the mouthpiece. And this is important because we've seen in high-speed imaging some mechanisms that explain the deagglomeration, but this tells you that this deagglomeration works, but the ball also helps with the particle recovery, which is good for your FPD. So I'll touch very briefly on the device performance. We've done tests with 3 emulated breathing profiles, emulating severe, moderate, and mild COPD on an escalating filling weight. And the important result here is that there is no collapse of performance of the engine as we increase the filling weight. And actually, if you look a bit closer to the data, it increases very steadily, but the main thing is that there is no collapse in performance with this engine. Another thing we've investigated is can we seed denser formulations in the device and see what happens. So in this case, powder A is a micronized formulation we've seen before. Powder B is a lactose-based formulation, so lactohel 200, 3 times denser, larger particles, and you can see that the particles accumulate even more on the edges because they are heavier, they are more subject to the centrifugal forces. But you see also impact on the destabilization of the cyclone by the cruciform ball. And this suggests that the mechanism we've seen is actually valid for different types of formulations and can be extended to denser formulation. And we've actually also investigated lighter formulation with a lower density. So to conclude, what we've seen in this presentation is a deagglomeration mechanism that relies on the chaotic dynamics of a cruciform ball in a cyclonic chamber. This has several beneficial effects on deagglomeration by introducing shear, by promoting impact of particles against the walls, but also by helping the recovery. We've investigated different types of formulation, which suggests that this mechanism is valid for a wider range of formulations than the ones I've presented here. And also, a good thing is that this design actually can be tuned to match potential different formulations and optimize the performance. I'd like to end by thanking the organizers for inviting us. It's my first time in person here. I think it's amazing. I'm very happy to be here. Thank you so much. I'd like to thank the team. We are here, booth 169. Several members who were here driving the project. So Andreas is here. Kellen, who came up with the ball, is here as well. Please come talk to us if you're interested. And thank you all for your attention.
Thank you, Baudouin. Another data-rich, really visually interesting presentation. Thanks for sharing that with you. I loved all those simulations and images. Have we got any questions from the floor?
Thank you, Arnaldo Ripamonti, Unifarma. My curiosity, did you try to put two small balls, different shape, instead of one, to see the chaos?
Yeah, so we've tried different shapes. I believe we've tried two smaller balls, but this one was the best performing one. It turns out it was giving the best results.
Thank you.
There are some reasons for this also on the shape. Since we are on the balls, it's a shape that maximizes drag. So it promotes a lot of deagglomeration also, like the corners, you could see their impacts against the ball. So it's very, it helps a lot with deagglomeration.
Thank you. You've got a question over there?
In a ball with a hole inside.
Yeah,
you try also.
Yeah.
Okay, thank you.
Hi. I was wondering, could you elaborate a bit on how you came up with this shape, especially, and if you tried some others as well?
Yes, we have. Yeah. It was exactly the question.
Thank you. Any other questions? I think we've probably got time for another question. Oh, over there. Thank you. Got to wave your hand up because it's hard to see from the stage.
Thanks. Great talk. I'm interested. It looked as though you might have slowed the plume down in terms of prolonging its timing compared with the no ball.
You think? So no, sorry. So I think. Okay, I think we've seen. So you're talking about the free.
I'm talking about the timing of the plume. You know, coming out, the speed at which it's the length at which it's extended, because that's often an interesting aspect that's not picked up in vitro, but has a huge impact on the pharmacokinetics.
Yes. So for these studies, indeed, we've extended the duration of the flow, but you're right, it has an impact. What we notice is that the evacuation is quite good, so all the powder goes anyway very quickly. We've done also some testing with realistic inhalation times, and it was giving the same. We were seeing the same things actually. A thing that's a bit misleading is there are very high-speed images recorded at 10,000 hertz. So you have a lot of frame, and the videos are really slowed down compared to the reality, which gives this impression of length, but it's actually a very fast phenomenon.
Thank you. If we've got, I think, one last quick one.
Yeah, I was just wondering, the circular balls seem to have the same uplift properties of the particle, but a stable cyclone. Was there any benefits that might bring?
So that's a very good question. The spherical ball is actually beneficial compared to no ball in the cyclone. But yet the cruciform ball is much better actually. So, and for these reasons. So the flow being destabilized by this chaotic dynamics is actually very beneficial because of the increase of shear in the flow. But you also have, I don't know if it was very noticeable on the high speed for the last one, on big screen, you have also lots of impacts against the surface of the ball because of the corner actually. So you have, when you compute the flow, you have a very sharp turn of the velocities, which means that it's so fast actually for the particles that they, by inertia, they will impact much more favorably the surface, while the spherical ball, we will more contour it and flow around actually. So you'll have less impact against the ball.
Okay, thank you.
Thank you.
We'll move on to our final talk of the day. But before we do, I'd just like to again thank Baudouin for his presentation. Thank you.